6-3 scale vectors in the plane, that basically just means we're doing two-dimensional vectors. Those of you that get deep enough into calculus and/or physics, you might get into three-dimensional vectors or even theoretical dimensions beyond 3 if you go deep enough. But a vector, it kind of looks like an array. If you remember from geometry, it has a definite starting point, and it goes a certain distance and has an arrow indicating direction. So the two things vectors have to have. They have to have a magnitude, they have to have a direction. So a good example of a scalar is just speed. Speed, if I'm going 70 miles an hour, well, if I don't know which direction I'm going, I could be going a lot of different places. But if I say I'm traveling south on the interstate at 70 miles an hour, now I've got a direction and a speed, so that's a vector. So scalar only has magnitude, that's it, no direction. Vectors tell you which way you're going and how fast you're going, or how much you're pulling, like a force, something like that. Now graphically, they're going to be represented as, like I said, kind of like an array. They do have a definite starting point, a definite ending point, and they do have a direction that they're heading in. Right? So if I went from here this way, that would be a completely different vector than the one you see right here. You're going to see the little, we always call it a hat. I really don't know what the name of the symbol is called. But you'll see this little kind of half arrow shape over top of a letter that indicates that letter, the variable represents a vector. Some notations you'll see with it. The magnitude, that's kind of the overall length. Common things, again, you'll see things like speed, pounds of force, newtons of force. The magnitude is the overall length, so we'll end up using distance formula to figure out how long this is, and that's what we'll use to represent it. You'll see it looks like kind of like absolute value, but with double bars. And in component form, this is what we'll work with a lot of the time, but there's another method later I'm going to show you that lends itself better to doing algebra. You'll see these kind of arrow-shaped brackets around it, pointy brackets. And it's kind of like a coordinate. It's going to have an x and a y component to it. And it's really just how far you go in the x and how far you go in the y. It's not a definite point. These things can start anywhere. Wherever they start, they go this far over, this far up. That's what that indicates. So just kind of make an example of this one. You're going over to the right 5. You're going up 2. And that would be your component form, 5, 2. Again, that shows you go over 5 and up 2. And you have those little pointy brackets. So let's do some actual work with multiple vectors and put them together. So let's say we've got a vector that's 4, 3. And again, that doesn't matter where it starts. Wherever it starts, it goes over 4, up 3. You got another vector that goes over 3, down 2. So I'm going to begin this graphically before I actually do it by hand, so it kind of makes sense. It's pretty easy to do by hand. But I've got some vectors already drawn out. Here's vector u. It's going, again, over 4, up 3. And it's really convenient to put at the origin. If it doesn't tell you where to start, you can start anywhere you want. It's just kind of a nice place to begin. And then once I get done with that vector, I put u or v right at the end of it, which is going over 3, down 2. And the overall result is from the beginning to the end of both vectors. It's kind of like if you drove this way for a while and then reached your destination and drove this way. Well, you ended up over here. You started here, you ended up there. So how far did you go? That's kind of the idea. And the resulting vector here would be 7, 1. Over 7, up 1. So let's do the algebra and let's see if we can come up with that. So the algebra is pretty straightforward. You're just going to add the x's together because ultimately you went over 4 and then you went over 3 more. And then you add your y's together. So that would be 1. You went up 3 and then later on you came down 2. Of course we saw that on the graph, so there you go, 7, 1. U minus v, pretty similar logic. Take the x minus the other x. So 4 minus 3 is 1. 3 minus negative 2 is 5. So I'm still going u to begin, but then I'm going negative v when I get to the end of that. So here's a negative v. It's v just going the opposite direction. And if you start at the origin, over 4 up 3, and then go back 3 up 2, you end up over 1 and up 5 from where you began. That's what we saw by the algebra. 3v, the 3 is what we call scalar, because it just has a magnitude of 3. It's stretching the vector 3 times bigger than it was. So all we're really doing is multiplying the x value by 3, multiplying the y value by 3. Graphically, it'd be like putting v together 3 times. That's really all it does. And then 2u minus 3v. So I'll do that in a couple of steps. 2u would be 8, 6. And then we're going to subtract from it 3 times v, which I just figured out to be 9, negative 6. So 8 minus 9 is negative 1. 6 minus negative 6 would be 12. And that would be your overall result. Right, unit vectors just lend themselves to doing algebra much better. So when you get into physics, you're probably only going to see the unit vector form. You're not going to see component much. Because really doing algebra with this stuff, and we just did one where we did the 2u minus 3v, it wasn't bad. But it starts getting kind of clumsy keeping everything inside of these brackets and kind of messing with them that way. This is just more natural to our algebra, but all we're doing is we're attaching the letter I to the x value of the vector, j to the y value of the vector. And if you get into 3 dimensions, you'll see a k involved. So it's just it's ij for x and y, basically. X amount, y amount. So component form has the pointy brackets. Unit vector form has ij. These two are just kind of there for technical details. I is going over 1 to the right horizontally. J is just going up, and that's it. So this is just 1 over, 0 up. J is 0 up, 1, or J is 0 over, 1 up. So just to kind of see how it's a little bit easier to work with vectors in this form, let's just do an example. So I've got 2 new vectors, u and v. They're given in unit vector form. If you really wanted to, and I don't want to for this example, but if I really wanted to, I could write these this way in component form. So just so you see the similarity there. But I want to find 2u plus v. So 2 times u, 2i minus 3j, and then plus v, which is 3i plus 5j. So just do your algebra, distribute the 2, so 4i minus 6j plus 3i plus 5j. And then we're going to get 7i minus j as our final result. Again, if you want to think about that as a component. All right, I did ask you to graph this, so let's take a shot at that. We can go with the over 2 down 3 idea in ij, or we can write it as a component if you need to think about that. But I am going to do 2 u's, so over 2 down 3 twice. So over 2 down 3, and then I'm going to do that one more time. So I'm at 4, negative 6 now. And I should probably label that, that's 2u. Now v was over 3 up 5. So from that point, over 3 up 5 puts me here. There's v. So the result, if you started here, you end up right there. You went over 7, you went down 1. And that's the result we also got, however you want to think about it, doing the algebra.